We're in section P5, okay? In this section, what we're going to look at are rational expressions, okay? Essentially, it's just going to be fractions of polynomials. Now, I'm pretty sure I said that last time, but that's really what it boils down to. They're just fractions of polynomials. So we'll see what they are. We'll also see how we can multiply and divide them and how to add and subtract them. You'll actually see that it's really just the same as adding and multiplying, dividing, adding and subtracting fractions. So same rules actually, which is nice. Okay, so what is a rational expression? Well, by definition, a rational expression, it's just a quotient of two polynomials. You know, it's a fraction of two polynomials. So in other words, it's something that looks like this, where P and Q are two polynomials. Here, as you can see, right? Okay. These are just some examples. You know, I have 1 over x, 1 over x squared, minus 1, and so on. In particular, just like any integer is a fraction of integers, right? Because you can divide by 1. Any polynomial is itself a rational expression. And why is that? Well, that's because for any polynomial, right, you divide by 1, you're not really doing anything in a sense. You just get the polynomial itself back. Okay? That's what we get here. Now, we did talk about domain, you know, the idea of a domain for a function. There is a domain of a rational expression, and it's basically all numbers except those where the denominator is 0. Except those where the denominator is 0. So in other words, if you have P of x over Q of x, right? Let's say you wanted to find the domain of this. So again, the domain is all x such that Q of x is not 0. So what you do is you first determine where it is 0, right? You solve that equation. And the domain is everything else. Basically, the domain is all numbers except the solutions to this. Okay? Here's an example. I mean, here's a little bit easy. It's not as bad, this one. And why is that? The denominator is factored. Right? So for this one, for instance, right? We want to know what the domain of this thing is. Well, we have x times x minus 2 times x plus 3 equal to 0, right? Okay? That's what we have here. So we have here equations. We have equations x equal to 0, right? We have x equal to 0. We have x minus 2. Excuse me. Sorry, I got ahead of myself. From this product, right? Remember, what do? You set each factor equal to 0. So we have x equal to 0, x minus 2 equal to 0, x plus 3 equal to 0. So really here you get 3 equations to solve. Although I guess really 2, because x equals 0, it's obvious what the solution to that is. For the other 2, like for x minus 2 equals 0, you just solve for x, right? You add 2 to both sides. You get x equals 2. From here, same idea, right? X plus 3 is 0. Solve for x. Subtract 3 from each side. So we get x equals minus 3. Okay? So here the solutions to this equation are 0, 2, and -3. The domain then is all numbers except 0, 2, and -3. So everything else is the domain. So that's what the domain would be for this rational expression. Okay, any questions on that? Okay, here's another example. Here, we want to find the domain of that rational expression, right? How do we do that? Well, again, we set the denominator equal to 0, and we solve the equation. Now here, we have a quadratic, right? Polynomial of degree 2. The leading coefficient's not 1. Personally, what I would do is just dive right into the quadratic formula, right? You can see we have A is 3, B is 5, C is 11. Okay. So in this case, we use the quadratic formula, plug the numbers in. We have -5 plus or minus, right? We have x equals -5, negative b plus or minus the square root of 5 squared minus 4 times 3 times 11. Okay, 4 times 3 times 11, all divided by 2 times 3. And basically, we do this, and what happens is you end up getting this. You get -5 plus or minus the square root of 25 minus 132 over 6. But that turns out to be this. Notice we have a negative square root here. That is, we're taking the square root of a negative number. That's not a real number, right? What does that tell us? This is never equal to 0. I mean, here we're only working in real numbers, okay? So there's no real number x such that this thing is 0. Hence, this thing is defined for all numbers x. That is, it's defined for all numbers. So the domain is everything. The domain is everything. All numbers. Yeah?
So does that mean the domain cannot equal all real numbers, or the domain includes all real numbers?
No, it equals all real numbers.
Oh, okay. Okay.
Okay, that's right. Because again, there's no solutions to this. That's what this is telling us, right? There's no solutions to this. So because of that, the domain is everything. This thing is never equal to 0, in other words.
Okay, thank you.
You're welcome. Good question. Actually, let me ask something. What's that? Ah, there it is. I want to do this. I haven't done this in a while. Just feel better asking this using a poll. You can be honest. If it doesn't make sense, say so. But if it does, say so also. So, okay. Thanks everyone who showed up though today. All right. Let me see. I guess. Okay. Everyone else, come on. All right. Well, let me keep going then. All right. All right. Anyway, let's keep going. So that's what happens here. So again, because, excuse me, from the quadratic formula, because we have the square root of a negative, that tells us there are no solutions to this. Okay? No solutions to this. So this thing is, so the denominator is never 0. So the domain is all real numbers, which you can write as an interval like I did. Or you could just write it out in words. All right. Just like you can write a fraction in lowest terms, we can do sort of the same thing with rational expressions. Essentially, we say a rational expression is simplified if the numerator and denominator have no common factors, except 1 and -1. 1, -1 are always going to be factors. You can't get around that. But if those are the only two, then it's simplified. And what's really nice is the factor theorem is very helpful here, right? Remember what that is. I wrote it here, right? For any polynomial p of x and any real number a, right? X minus a is a factor of the polynomial if and exactly when p of a is 0. That's going to be helpful here. Sometimes what can happen is, well, let me say this first. To simplify, what you would have to do is factor the numerator and denominator. I mean, sometimes you don't have to factor both. You can use the factor theorem. So sometimes what you can do is you can factor the numerator if it's easier to factor, and then use the factor theorem to see if the numerator and denominator have any common factors. And if there are any common factors, you cancel them. I mean, in reality, what you're doing is you're dividing, but you could just cancel. And you could factor top and bottom if you want to, numerator and denominator. What I'm saying is with the factor theorem, you may not have to, which is nice. Saves you some work. Okay. Do this.